Welcome back. Our second generative models in the deep dive into generative models is Generative Adversarial Networks or GANs, and also we'll look at some advanced GAN variants. In this video, we will cover generative adversarial networks as understood by a 10-year-old. Then we're going to look at some generative adversarial network basics, and finally, we'll deep dive into generative adversarial networks. So to start with, let's go over generative adversarial networks as understood by a 10-year-old. Alright, imagine you have two friends who love to play games. One is really good at making up pictures. We'll call this friend the artist. And the other is great at spotting fake ones. We'll call this friend the judge. They decide to play a game together to make each other better at their skills. Now, how the game works, or GANs, the artist or the generator job is to create pictures from scratch. At first, the pictures might be really rough and don't look very realistic. But every time the artist makes a picture, the judge takes a look and tries to figure out if it's a real picture or a fake one. On the other hand, we have the judge, discriminator. The judge's job is to decide if the picture is real or fake. Real pictures come from actual photos, while fake ones come from the artist. At the start, the judge can tell that the artist pictures are fake because they don't look quite right. Now let's see how they're playing together. Each time they play, the artist learns from the judge's feedback and tries to make better pictures. And the judge gets better at spotting fakes. They keep playing until the judge can't tell the difference between real photos and the artist's picture anymore. That's when they know the artist has gotten really good. So let's look at some advanced artist skills or advanced GN variants, which we'll be covering later on. Over time, some artists get really good at different styles and tricks, and they can even do special things with their drawings. Let's meet two of them. One is StyleGAN, the super detail artist, and the other one is BigGAN, the variety pro. So let's go deep into StyleGAN. The StyleGAN is like an artist who's learned to add super fine details. Imagine this artist can choose exactly how big someone's eyes should be, the color of their hair, or even make little details like freckles. StyleGAN can even mix and match styles, like combining someone's face shape with someone else's hairstyle. It's amazing for making super realistic faces or even creating cool new designs. Next, let's look at BigGAN, the Variety Pro. BigGAN is like a artist who's great at making lots of different things like animals, cars, and buildings. If you asked BigGAN for a picture of a lion, it can make all kinds of lions that look real. BigGAN also learned a special trick called the truncation trick, which helps it make pictures that are best quality even though they are all a little different from each other. Why are these artists so cool? Artists like StyleGAN and BigGAN or StyleGAN and BigGAN are used by game designers, movie makers, and scientists to create super realistic pictures or even just fun creative designs. People can use these pictures for games, in movies, to create backgrounds, or even for art. It's like having a super talented friend who can make anything you imagine. And that's how GANs, StyleGAN, and BigGAN work. It's all about two friends, the artist and the judge, helping each other get better and creating amazing things. Now that you understood the crux of what generative adversarial networks are, let's dive into generative adversarial network basics. Generative adversarial networks, GANs, are a type of deep learning model used to generate realistic synthetic data such as images, videos, and audio. Introduced by Ian Goodfellow and his team in 2014, GANs consist of two neural networks, the generator and the discriminator, working in opposition to each other. The generator creates fake data, while the discriminator evaluates the authenticity of this data. Through iterative training, the generator improves its ability to produce realistic data until the discriminator can no longer distinguish it from real data. Some of the key concepts of GANs include: first, the generator takes random noise as input and attempts to generate realistic data such as an image. Then we have the discriminator, takes data which is real or generated and classifies it as real or fake, providing feedback to the generator. We have adversarial training. Both networks are trained simultaneously in a zero sum game. As one improves, the other adjusts, resulting in more refined outputs over time. Let's look at some advanced GAN variants. Several advanced GAN architectures have been developed to address specific challenges, enhance performance, or improve image quality and resolution. We have StyleGAN. StyleGAN is an advanced GAN variant introduced by NVIDIA, specifically designed for high quality photorealistic image synthesis. It has been widely used in generating detailed human faces. Style-based generator. StyleGAN introduced a style-based generator that allows for more control over the generated images by altering specific styles at different levels of image synthesis. This enables fine-grained control over aspects like texture, color, and shapes. We have progressive growing. Like progressive GANs, StyleGAN uses progressive growing techniques for higher quality images. Applications. StyleGAN is popularly used in art and design fields and in applications where detailed synthetic faces or complex scenes are needed. BigGAN. BigGAN is an advanced GAN designed to produce high resolution images with improved diversity, often trained on ImageNet. Larger architecture. BigGN incorporates larger architectures and more compute power to improve fidelity and diversity in generated images. Class conditioning. BigGN allows for class conditioning, meaning the generator can generate images of specific objects. Example can be a dog, a cat, resulting in diverse class specific high resolution images. Your stable training. BigGN introduces techniques for stable training at high resolutions, such as balancing batch sizes and implementing advanced normalization techniques. Let's look at some other GAN variants. We have DCGAN, known for stable GAN architecture using convolutional layers, useful for generating realistic images. We also have cycle GAN, which transforms images from one domain to another. Example, converting photos into artistic styles. We have pix to pix. This is image to image translation where the GAN is trained on paired image data. Example, converting sketches to colored images. Next, let's look at some applications of GANs and advanced variants. Image synthesis is one, creating realistic faces, landscapes, or objects. Can be used for art and media, generating artwork, video game assets, and even music. Can be used for data augmentation, generating more data for training other AI models, especially in limited data scenarios. Medical imaging, assisting in creating synthetic but realistic medical images for training purposes. Let's talk about the challenges. GANs can be challenging to train, prone to instability, and can suffer from issues like mode collapse, where the generator produces limited variance in outputs. Advanced GAN architectures help mitigate these issues but often require significant computational resources. Next, let's deep dive into generative adversarial networks. So let's talk in depth about generative adversarial networks, GANs. GANs are a class of deep learning models where two neural networks, as I mentioned, the generator and the discriminator, compete against each other in a game theoretic framework. This unique setup results in the generation of realistic data by continuously improving the quality of generated outputs. Let's take a closer look at GAN's framework and its working. So let's look at the architecture and mechanism. First, for generator. The generator is tasked with creating synthetic data from random noise, typically sampled from a uniform or Gaussian distribution. Its goal is to generate data that appears indistinguishable from real data. Through training, the generator learns how to transform random noise into structured data by minimizing a loss function influenced by the discriminator's feedback. Let's talk about discriminator. The discriminator is a binary classifier that evaluates the authenticity of the data. It receives both real data from the dataset and fake data from the generator and attempts to distinguish between the two. The discriminator maximizes the probability of correctly identifying real versus fake data, improving as the generator becomes better at creating realistic data. Let's talk about the training process, also called as the adversarial learning. GANs are trained in zero-sum game where the generator tries to fool the discriminator and the discriminator tries not to be fooled. This process is iterative. The discriminator trains on both real and fake samples to increase its accuracy. The generator then trains to produce better data to fool the discriminator. The objective is to reach a Nash equilibrium where the discriminator can no longer distinguish real from fake, meaning the generator produces data that is indistinguishable realistic. Let's talk about some of the challenges in GAN training. One is mode collapse. The generator may produce limited variations, ignoring other potential modes in the data distribution. We have non-convergence. Due to the adversarial nature, GAN training can be unstable and difficult to converge. We also have vanishing gradients. The discriminator's feedback can diminish, making it hard for the generator to improve. Let's talk about the advanced GAN variants. To overcome the different challenges that we discussed earlier and expand GAN capabilities, several advanced variants have been developed. Let's explore StyleGAN and BigGAN, two popular architecture for generating high-resolution diverse images in more detail. Now, first, StyleGAN, which is, as I mentioned, developed by NVIDIA. StyleGAN is specifically designed to generate photorealistic images with fine-grained control over various features. Some of the key innovations include style-based architecture. Now, the traditional GANs map random noise directly into an image, but StyleGAN introduces an intermediate layer called the style vector, which manipulates various attributes of the generated image. This architecture separates high level aspects, example face shape, from fine details, example texture, allowing for greater control over generated features. Adaptive instance normalization, or ADAIN. ADAIN adjusts the feature maps based on the style vector, allowing specific control over image attributes at different layers in the network. This technique enables StyleGAN to adjust styles hierarchically, with lower layers affecting more global aspects of the image and higher layers fine tuning details. Your progressive growing. StyleGAN uses progressive growing, gradually adding layers to the generator and discriminator to stabilize, training, and improve image quality. This method enables StyleGAN to generate high resolution images more effectively by training the network to first generate lower resolution images and then gradually increase the resolution. Let's look at some of the applications. StyleGAN is widely used in art generation, synthetic face creation, and application requiring high quality and detailed synthetic data. Let's look at the next one, which is BigGAN. BigGAN, developed by DeepMind, is an advanced GAN variant designed for high resolution image synthesis with improved class diversity. Some of the key innovations include large batch sizes and compute resources. BigGAN utilizes extremely large batch sizes and computational resources during training, which helps stabilize training and improves both image quality and class fidelity. These larger batch sizes allow the model to learn more robust representations, especially useful for generating diverse classes of images. Class conditional GAN. BigGAN is a class conditional GAN, meaning that the generator can produce images of specific classes, example animals, objects. Class conditioning is achieved by incorporating class labels into both the generator and discriminator, allowing for more controlled image synthesis. Then we have the truncation trick. To improve sample quality, BigGAN introduces the truncation trick, which limits the range of latent vectors. This constrains the generator's output to a narrower, higher quality subject of images. The truncation trick allows BigGAN to balance quality and diversity, adjusting the level of truncation for the desired outcome. The applications for BigGAN include BigGAN is extensively used in visual research, art, and creating high resolution datasets, as it can generate diverse images with high fidelity across numerous classes. Let's look at comparisons and use cases. StyleGAN versus BigGAN. We have control and detail. StyleGAN excels in cases where fine control over specific image attributes is required, such as facial feature modification. It allows for detailed manipulations at various hierarchical levels of the image. Diversity and class conditioning. BigGAN is ideal when generating diverse classes of high quality images, making it suitable for scenarios requiring multiple categories of synthetic data. Resource requirements. Both models are resource intensive, but BigGAN in particular requires substantial computational power due to its large batch sizes. Let's look at some broader applications of advanced GANs. We have media and entertainment, generating synthetic backgrounds, faces, and assets for movies, video games, and virtual environments. We have data augmentation, producing additional training samples for machine learning tasks, especially used in medical imaging or rare event prediction. We have art and creative design, enabling artists and designers to explore creative possibilities by generating unique and stylized visuals. Scientific research. GANs help in creating synthetic data sets that preserve privacy or generate hypothetical scenarios for analysis. Let's talk about challenges and future directions. While GANs have achieved impressive results, challenges such as stability, interpretability, and ethical concerns still remain. Current research is exploring methods like self supervised GANs, GAN inversion for image editing, and integrating GANs with other models like transformers for improved synthesis capabilities. In summary, advanced GAN variants like StyleGAN and BigGAN extend the boundaries of what GANs can achieve, providing high quality, diverse, and controllable data generation capabilities. They remain a powerful tool in machine learning, influencing fields from creative arts to scientific research.